Okay, so this is the video on equilibrium. Here we are going to really just have some fun. This is one of my favorite units because it seems like it's going to be really complicated, but when you really think about it, it becomes a little bit more simple, and it's just our perceptions that make it hard. So we're going to look at equilibrium constants, and we're going to evaluate both those and reaction quotients from experimental data. Just by looking at the number, we can tell whether the reaction is going to be reactant-based or product-based, meaning what's going to be left over or primarily in the flask at equilibrium. We're going to do some quantitative studies, but I'm telling you guys, the math that we're going to be doing is actually kind of fun because we make some assumptions and some estimations that just kind of keep the math relatively simple. Then we're going to look primarily at Le Chantillier's principle, which says, you know, if you apply a pressure, how is it going to affect the overall system? So we're going to start off with chemical equilibria. We're just going to talk about what does it really mean, and then we're going to get into some equilibrium constants. From there, we'll maybe in the next video do Le Chantillier's principle and really talk about calculations in the next video as well. Now, chemical equilibrium is the concept that's going to dominate the next few units, and it's because we talk about in 111 about how, oh, you have A reacting and it goes to B. Well, that's true sometimes. You can't unexplode something, and you can't always go backwards. You can't undo a chemical reaction. You can't unburn wood, for example. However, for a lot of reactions, it's a reversible process. And so, for example, we need to be able to consider whether we are actually going in this forward direction or in the reverse direction. And then we also need to consider how the concentrations of these two things at equilibrium are going to be pretty stagnant. Now, microscopically, equilibrium is pretty dynamic. You have A turning to B and B turning to A. You have reactants reacting to make products, products reacting to remake reactants continuously. It's always going on. Meanwhile, on a macroscopic level, it's going to stay pretty static. And so you have, like, in general, a flask, and what's going to happen is it's going to look as if nothing is happening. But even though, you know, say you had a solid here and maybe some of it is dissolving, but if it's super saturated, some of it is also going to be precipitating back out. So you have things shifting all the time, but it's going to look the same. This is going to look the same size. It's going to look like the same amount is precipitated out. It's going to look like the same amount of reactant, the same amount of product, as long as it is at equilibrium. If it's at equilibrium, it really doesn't look like anything's happening, even though it is. So here, if we look here, we've got dinitrogen tetroxide reacting to form 2 moles of nitrogen dioxide. Well, just like when we were talking about kinetics, you start off, you have all reactant. And you start off with all reactant, and over time that deteriorates. And eventually you become constant. Meanwhile, at the beginning you have 0 product. And at some point you make some. And at equilibrium, you have the same amount of both of those guys. No. Let me restate that. You do not have the same amount. You have a static amount. The amount of reactant is not changing. The amount of product is not changing. Even though it looks as if the reaction has stopped, it is not. You have the forward reaction happening. You have the reverse reaction happening. It's just that now they are happening at the same speed. And so you do have reactant being made, you do have product being made, but overall their concentrations are static here. So at equilibrium, the concentrations of both reactants and the products are constant. It does not mean that they're equal. It doesn't mean that they're high or low. It just means that they do not change over time. Now, what that really implies is that the reaction rates of both forward and reverse reactions must be the same. Now, I can't actually do this. I've been in contact with tech support for a couple days now. For some reason, this won't open. I think I could do it at home, but that's beside the point. Now guys, when you open this video, go ahead and hit pause and open this video. It is amazing. It walks you through everything that we talked about with kinetics, and then it leads right in to equilibrium. It talks about why we have to consider reversible reactions. It shows you why things look static on the macroscopic level while being microscopically dynamic. It shows you this. This is a great video. They made it, I actually came across it last year. It's just fantastic. So, unlike kinetics, the equilibrium constant is going to be derived straight from your balanced equation. And so you're going to have the concentration of your products over the concentration of your reactants, each raised to the exponent of the coefficient in their balanced equation. Now, you'll notice here that our equilibrium constant is a capital K. Capital K, lowercase k is kinetics. Here we're doing capital K. Because it's products over reactants, if K is greater than 1, it is going to be product favored. It means that in this fraction you have more product than reactant. If K is less than 1, it means you have more reactants floating around in that flask than anything else, and so it's going to be a reactant favored reaction. So the value of K larger than 1 means that the reaction system is going to have mostly products once it reaches equilibrium. We also occasionally say that that means it lies to the right. You could also consider it that the reaction is basically happening to completion. You're making a lot of products. If you have a small k, meaning smaller than 1, the flask is going to have primarily reactants. It is going to have an equilibrium position to the left, and the reaction doesn't really happen very much. So equilibrium lies to the right. What's the value of K? Hit pause, but hopefully you know that K, if it's lying to the right, must be product favored and should be greater than 1. If the equilibrium lies to the left, hit pause, but hopefully you will see that if it lies left, it means you have mostly reactant, which is going to be the bottom of that fraction, so K should be less than 1. Now, in terms of how we're going to deal with the equilibrium constant, this is a little bit different than what we've done in previous units. Here it's all about the math. And so if we consider, for example, the reaction A reversibly going to B, the equilibrium constant for this is going to be K is equal to B over the concentration of A. Now, if we were to consider, this is just the forward regular way. Oops, go away. Stop. If we were to consider the opposite, B going to A, well, K here is going to be, now my product is A over B, which is now my new reactant. Considering the reverse reaction, guys, these are just reciprocals. So reciprocal means you're going in the reverse direction. If you were to multiply the, so this is KF, this is KR. Multiply the equation by something. So let's go ahead and consider again A going to B, where K is going to be B over A. These brackets mean concentration. At some point I will get lazy and I'll just start writing parentheses, but it does mean concentration in terms of molarity. So just keep that in mind for a minute. Now, If we were to multiply this by 2, so 2A reacting to form 2B, now we have this K is going to be B raised to that power of 2 over the concentration of A raised to its power of 2. So K2 ends up being K1 squared. So when you multiply a reaction by n, it ends up being that the K is raised to that exponent. Okay? Now, two great things here. We don't care about the units of K. Unlike kinetics, we just want the number. Is it bigger than 1, less than 1? We don't care. We just want to know what it is. In addition, no. Great. K doesn't change. K does not change as long as the temperature is constant. And so when we have our K value, it is going to be the same. So we don't really care that molarity is temperature dependent because we're going to be dealing with the same temperature. So K is always the same at a given temperature regardless of the amount of reactants or products that are present initially. Because we're talking ratio, guys, it doesn't matter if we're talking about 0.1 molar to 0.2 molar or 1 molar to 2 molar. The ratio is going to be the same. So it's a unitless number. Now for a reaction, because concentration doesn't matter, there's a lot of equilibrium positions depending on your starting concentration. But there's only one equilibrium constant. And you guys are going to see that in lab. You're going to see that no matter what solution you make, no matter what concentration of things you start with, the equilibrium constant, especially when you get to lab 8, is going to be the same no matter what. So like, well, we'll get there. Now, homogeneous equilibria are pretty easy to deal with. That means all gaseous or all aqueous components. Now, the equilibrium concentration, the equilibrium constant deals with concentrations. Because you can only talk about molarity in terms of gases or something that is dissolved, you cannot use either liquids or solids. You can't do it. So it has to only be gases or aqueous that you can plug into this. So go ahead and hit pause and write your K for both of these reactions. Okay, so when you come back, the first thing you need to do is make sure that you've got a balanced equation, otherwise it doesn't do you any good. Over here I have 2 nitrogens, 3 times 2 is 6 hydrogens. On this side, 2 nitrogens, 2 times 3 is 6 hydrogens. Now technically I'm not going to have a question about balancing. That was 111 stuff. However, occasionally I make a mistake, so make sure it's balanced just to, so I'm not accidentally setting you up. So here, if we were to write this, it's going to be products over reactants. So it's ammonia raised to the 2nd power over our reactants, which is N2. There's only a 1, so we don't need to worry about that. Multiplied by the concentration of hydrogen cubed. Down here, aqueous, 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 they are all going to go in here. Let's make sure that we are balanced. 1, 1, 1, 1, 1, 1. We're good. So here, products are going to be H plus raised to the 1 power times the concentration of cyanide raised to the 1 power because its coefficient is 1. Over the concentration of HCN. And just like that, we have our equilibrium expression. Heterogeneous equilibria are when you have something that, like a liquid or a solid that is not going to be included in the equilibrium expression. So you're only going to deal with the gases or the aqueous components. So go ahead and hit pause here and write your equilibrium expression for both of these, please. Okay, and coming back, we're going to put products over reactants. So products, we don't care about the KCl, it's a solid. So we're going to have the concentration of O oxygen raised to the third power. Same thing, we don't care about this because it's a solid. So the equilibrium constant is equal to the concentration of oxygen cubed. Down here, we don't care about this guy, it's a liquid, it can't go in our equilibrium expression. So our K is going to be equal to products H2 squared, because that's its coefficient, times the concentration of O2. Just like that. Now, because the position does not depend on solids or liquids, it's going to make it a little bit more interesting when you write the equilibrium expressions for these reactions. Just make sure you're paying attention to choose state or phase of matter, either way. All right, so go ahead and hit pause and write the equilibrium expressions for each of these reactions. I am going to assume that you have hit pause and you are coming back, and I'm going to deal with this. So K, I'm going to look, all gas. I do a tally, there's 1 carbon on each side. 4, 3 plus 1 is 4, 2, 1 and 2. This is a balanced equation. So now I'm going to put products over reactants. So CH3Cl, there's a 1 here so I don't care, times HCl over CH4, methane, times Cl2. Just like that. Now, for this guy, gas, 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 they're all going to be included because they're all a gas or aqueous. If I count 2 nitrogens, 2 nitrogens, 2 oxygens, 2 oxygens, so this is a balanced equation. I'm just going to put products, which is my nitrogen monoxide. It's got a 2 here, so it's going to be squared, over the concentration of nitrogen gas times the concentration of oxygen gas, just like that. For barium sulfite reacting to form barium oxide and sulfur dioxide, if you look, this is a balanced equation, 1 barium, 1 sulfur, 3 oxygens, 1 plus 2 is 3. But this is a heterogeneous situation. So I'm not going to include these components that have a solid. So those are going to be omitted. So K is always products over reactants. So SO2 is the only thing that counts, and it's a product, so it goes on top. Now down here, P4 reacting with 5 moles of O2 to produce P4O10. 4, 4, 5 times 2 is 10, 10 oxygens, this is balanced. Same thing, gas, gas we care about, we can't use our solid. So K is going to be equal to, well, none of our products count, so it's got to be 1 over the reactants. So it's going to be P4 times the concentration of O2 squared. I'm sorry, to the fifth. I'm really sorry, guys. Now, okay, for this guy, this is balanced, so we're going to put our products, which is Br squared, because of this 2, over Br2 concentration, like that. And now we have our equilibrium expressions for all of these. If we do the equilibrium expression for these, go ahead and hit pause and write those out. For this one, you have gas, gas, gas. So you're going to put products over reactants. So you have NO squared here. For barium oxide reacting with sulfur dioxide to make barium sulfite, K is going to be equal to, this product doesn't count, so it's just going to be 1. This reactant doesn't count, so we leave that out. Concentration of SO2. For this one, we don't care about that. So our K value here is just our products, which is P4, times the concentration of oxygen to the fifth. Now if we look, NO reacting to give nitrogen and oxygen is the exact opposite of this. So we've got NO squared over nitrogen and oxygen. Here we've got nitrogen and oxygen over the square of nitrogen oxide. They are inverse. It's a reverse reaction, so our K values are reciprocals or inverse of one another. If you need to, you can kind of see again, K is equal to the concentration of SO2. K of the reverse is equal to 1 over SO2. They are reciprocals of one another because they are the reverse reaction. Now, it's great that you can set up the equilibrium expression. That's actually half the battle. But now we need to do some math with it. So let's go ahead and look at the K for this reaction. Here we've got methane reacting with a mole of chlorine gas to produce chloromethane and hydrochloric acid. Now, equilibrium expression for this is going to be K products CH3Cl times HCl, both gases so we care, over methane and Cl2, just like that. Now, if at equilibrium you get the concentrations, and you actually will in lab, you're going to be getting those calculations, those concentrations from your spec, you can plug them in. And so we tell you at equilibrium the concentration of methane is 0.2 molar. Concentration of chlorine is 0.4 molar. Concentration of HCl is 1.2 molar. And the concentration of chloromethane is 0.75 molar. Now, this is actually a really nice calculation because there's no exponents here. Because all the coefficients were 1, we don't have to worry about any exponents. So in your calculator, you just have 0.75 times 1.2 divided by 0.2 and divided by 0.4. And you end up getting something like 11.25. That's okay. Your K value can range from, 1 to the negative 10 to, I don't know, 100 billion. Those are the numbers that you may see this semester. This 11.25, if we consider an 11.25, this is bigger than 1. And so we can tell that if we were to mix methane and chlorine gas together, it's going to be a product-based reaction. So at equilibrium, we're going to have a lot more chloromethane and a lot more hydrochloric acid than either of our reactants. Calculate the equilibrium constant for the following reaction. If at equilibrium, the concentration of phosphorus is 2.15 molar and oxygen gas is 1.75 molar. Go ahead and hit pause here and actually try to calculate it out. I'm going to assume you have done that and you are coming back. Let's go back to red. Our K here is going to be products over reactant, so it's P4, O10. Except we don't care about this because it's a solid. Instead of writing it out like that, I'm just going to go ahead and put it as a 1. I thought it might be visually nice, but I changed my mind. These two are gases, so we do care. So it's P4 times O2 raised to the 5th power. Because we are given the concentrations, we're going to say it's equal to 1 over phosphorus is 2.15 times 1.75 concentration of oxygen raised to the 5th power. So you end up getting in your calculator 1 divided by these numbers. There's a couple of different ways that you could look at this. The big thing here, guys, is to make sure you actually get the right number. I can't tell you a number of times people will think that the math is easy and therefore they don't check that they're getting the right number in their calculator. So the big thing here, 283, I think, is that you make sure that you enter this and you're getting this number. You have to be smarter than your calculator. And so you can either say 2.15 times this guy 5 times or to the 5th power, and then do 1 divided by your answer that way. Or you can say 1 divided by 2.15 divided by 1.75. If you don't know how to do the 5th power, this is another option. It is telling your calculator 1, 2, 3, 4 that you are smart enough to know your order of operations is 1 divided by this and divided by 5 of those. Either way, as long as you are getting this, you will be fine. Now here, your K is less than 1, so this is going to be reactant favored. So you're going to have a lot more reactants floating around in that vessel than you would products. Now let's see, how long is that video? Let's go ahead and leave it here. At this point, I'll go ahead and wrap up. We now know what an equilibrium constant looks like, how to write the expression for it, as well as what it means. I will continue with the rest of this unit in the next